So you quite often get these problems that are looking at a plane getting inclined, and then it's looking at for when something will start to slip. And it's all about the friction. And so what we've got here is the coefficient of friction between gravel. So we've got the gravel here, and the base of a tipper truck trailer is 0.25. So that's the coefficient of static friction, presumably. Ignoring the friction between the sides, the gravel and the sides of the trailer, we want to find out what angle theta the gravel will slide out at. So what I wanted to do for this was just have a look in a bit more detail about what's happening as you slowly increase this angle of inclination of this object, or this gravel. Could be anything. Could be a block of concrete or whatever. Now, we looked at this a little bit already when we did the figuring out the static coefficient of friction using a plank and increasing its angle. But let's just have a look at it in a little bit more detail here. So we've drawn a free body diagram. I've got two free body diagrams, one at quite a low angle and one at a steeper angle. And let's just see what happens here. And so what we're interested in is we've got the weight, that's the applied force, it's just the weight of this gravel. It would be applied at the centroid. And the way we usually solve these problems is to split that into its components perpendicular or normal to the surface, and then also a component that's parallel to that surface. So we're going to split that weight up. Let me just think, what was it, 79, I think. And so we're going to have a component like so. So we'll call this one W. This might be WY. And then we're also going to have an X component. We'll dash that one because it's not at the right point of application. So we're going to have a component this way. It'll be, let's just show it at the right point of application, which is up here. And that'll be WX. Now, to have static equilibrium, we're not going to worry about moments. We'll get to that in the next one. But what we do know is that the sum of the X components must be 0 and the sum of the Y components must be 0. So therefore, we must have a reaction somewhere perpendicular to the surface like so, which is going to be our normal force. So our normal reaction. So this is just going to be like so, and it must be equal and opposite to WY. So it must be equal and opposite to this. And then our frictional force is going to be equal and opposite to WX. So it must be acting this way. And those two things would also give you a resultant. And the resultant would be equal and opposite to the original weight. So the resultant would end up being something like this. Now, if you look at your angles rules, you'll be able to figure out that this is also equal to theta. And this is not too well drawn, but anyway, this here is also equal to theta. Okay, the angle between that resultant force. And so this angle theta, well, it's theta 1 in this case. So we've got theta 1, theta 1, theta 1. Now, what you can see here is when you've got a low inclination, you've got quite a low force parallel to that slope. So you've got quite a low force wanting to make this slip. And you've got quite a high normal force. And you remember, and so, well, let's just leave it at that. You've got a high normal force, low force parallel to that slip plane. And so therefore, it's not much one to make that slip down. But if you increase the angle further, so the weight's still going to be the same. So it's not going to change. It's going to go straight down. It's going to have the same magnitude. But this time when we split this into its components, the normal force has dropped. Let's just see what I've drawn this as. It doesn't mean anything, that 26 is just what I've drawn it as, so that must be 64. And so now you've got WY is a wee bit less, and WX is now increased. So it's now getting a bit bigger, and its actual point of application would be up here. And still, this angle here is now theta 2. And then we're going to have some reactions to this. So we're going to have reaction in the y direction, which is equal to Wy. And that's just going to be our normal force. And we're going to have reaction to the X component. Which is must be equal and opposite to the, so this is our force, our frictional force, and it must be equal and opposite to Wx. And again, they would give you some resultant force. I don't know if that really matters or not. Probably not. I don't know if I even really need to draw that resultant force. That's okay. So let me just rub that out. So what's going to happen is eventually you're going to get to the point, so remember here, so as you increase the load that's going parallel to the surface, the frictional force matches it, so you've got static equilibrium until it gets to the point where it can't get any bigger, that frictional force, and at that point that frictional force is called Fs, the static friction. And so this here is going to be Fs. Yeah, I didn't really need to draw this on here. I'm just going to get rid of that to make that a bit simpler. And so this is just going to, this one here we haven't got to that limit yet, so this is just F, this is just N. But what we do know is that that normal force N is equal to Wy, and that frictional force F is equal to the X component of the weight. Similarly here, now what we're saying here is we've got to the angle, θ2 has got up to the angle where this frictional force has reached its limit. So we're at this point on the diagram. And so at that point we say, well, this frictional force is now called the static friction, Fs. The normal force is equal to Wy. And so let's just have a think about that. So, just do it in black. So Fs is equal to Wx, and the normal force is equal to Wy. What am I trying to do here? So, what else do we know? Well, we know that once we get to the point of slip, this is a Fs, and at that point of slip, Fs is equal to mu times n. So at slip, Fs is equal to mu s times the normal force. That's cool. Now, we also know that θ2, so this θ is just equal to, so this here is Wx. So it's just equal to Wx over Wy. So let's write that down. So tan θ2 is equal to that. So let's just say tan θ. Okay, I only really did these to show a couple of different examples. We'll just show that as θ. So tan θ is equal to Wx over Wy, and that is equal to tan θ at the point of slip. Wx is going to be Fs. Wy is going to be the same as this normal force here. So Wy here must be balanced by the normal force over n. So therefore θ is equal, and this is just equal to the static coefficient of friction from up here. So mu s is just Fs over n. So that's equal to mu s. Therefore θ is just tan to the minus 1 of mu s. And so in our case, and in fact, this is just the angle of friction. Okay, so we've just come back that full circle. So we're just seeing what's going on here, and let's just finish it off. So in our case, θ is going to be tan to the minus 1 of 0.25 was our static coefficient of friction. Let's just double check that. Yep, 0.25. So therefore, θ is going to be, I think it's about 14. Tan to the minus 1.25 is equal to 14.0 degrees. So it's going to just start slipping about 14.0 degrees. So let's go back through what we're talking about here. So as we tip this up, what happens is you've got the weight always acts straight downwards, but as you tip this up, this X component of that weight becomes larger. So you can see that by comparing these two. As this angle increases, the X component becomes larger and the normal force becomes smaller. Now, up to a certain point that we can generate that force. And so we're running up this part of the graph. And then we get to the critical point where that frictional force is equal to the static friction. And the normal force just equal to the normal force, just equal to the Y component of that weight. And because of that, we can show, just as we've shown here, that the angle at which it slips is just going to be tan to the -1 of the static coefficient of friction, which is kind of what you expect, and this is the angle of friction. And so an even quicker way is just to remember that the point at which it's going to slip is going to be the angle of static friction, is the point at which it's going to start slipping out of that trailer. Okay, we'll push on to the next example.